Definition of a horizontal asymptote. The line y equals L is a horizontal asymptote of the graph of f when the limit as x approaches negative infinity of your function equals L, or when the limit as x approaches positive infinity of your function equals L. The top limit refers to the behavior of your function for really negative x values. The bottom limit refers to the value your function takes as x gets really positive. These values don't have to be the same, but they are the same if your graph takes on the same value when x is really negative or really positive. Theorem 4.10 out of your e-text, limits at infinity. Number one, if R is a positive rational number and C is any real number, then the limit as x approaches infinity of C over x to the R equals 0, and the limit as x approaches negative infinity of C over x to the R equals 0. The graph that you see is just one illustration of these limits. I picked the function 1 over x squared as a representative. There are many other functions that fit this description. This is just one of them. Limits at infinity are investigating behavior in the really negative and really positive x value sections of a function's graph. For these particular types of functions, your limit value will be 0 in both cases. Number two, let me see if I can adjust that for you. All right, let me try that. Okay, so back before I get to number two, the second limit is valid only if x to the r is defined when x is negative. Number two, the limit as x approaches negative infinity of the function e to the x equals 0, and the limit as x approaches positive infinity of e to the negative x equals 0. Now, there's some handwritten limits I'm going to get to that weren't part of your e-text, but I'm going to go ahead and cover both of them. This top section here, both of these limits, look at the bottom left of your screen. If you take the graph of e to the x and draw it out, when your x's approach negative infinity, you're way out here on the left end, your limit is approaching 0. And that's what this limit states. What it didn't state was as you work your way into the positive x's, the farther right you go, or towards positive infinity, the higher or larger your function values go. That limit as you approach positive infinity does not exist. There's no finite value that your limit approaches. For the bottom set of limits, look at the graph of y equals e to the negative x. That can also be written as 1 over e to the x. This graph, when x approaches positive infinity, you come over here far to the right side, and your function is approaching 0 as x goes to positive infinity. That's this first limit. The one that I hand wrote is if you go into the negative x's. The farther negative you go with x, the larger your function value gets. So we have another case of a limit that doesn't exist. I just wanted to show you both ends of each function's graph to try to illustrate these limit values. Let's look at some guidelines for finding limits at positive and negative infinity of rational functions. Case number one. Oh, and before I forget, rational functions, that's just a fraction or a ratio of polynomials. Number one, if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. This first limit illustrates number one. We have 2x to the first plus 5 over 3x squared plus 1. The degree of the numerator is 1, which is less than the degree of the denominator, 2. When x gets really large, squaring a large number is really large compared to just the large number itself. Anytime your denominator goes faster than the numerator, your limit will approach 0. Number two, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. All I did in number two was I moved the power of x in the top from 1 to 2, making those degrees equal. As x goes to positive infinity, these constants of 5 and 1 will not matter that much. You want to look for your dominant terms. If they're the same power or degree, then you take their lead coefficient. So this would have a limit of 2/3. And then finally, number three, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. Once again, I'm going to make one modification, and I'm just going to make the denominator smaller than the numerator. So I've changed this power one higher to a cube. Cubing a large number is way larger than, squaring a large number. Since the numerator is going to get larger faster, this limit doesn't exist. Those values will continually get larger and larger. Now let's go back and do some basic limits, look at some properties. In our first limit, we have the limit as x goes to infinity, 5 minus 2 over x squared. As x goes to infinity, we can split this up and take limit of 5 minus limit of 2 over x squared. The limit of a constant stays the same, so that limit is valued at 5. The second limit, when x gets really large, this goes back to the previous slides where we had a constant over x to some rational number. In fact, it's just 2 for this one. As x gets really large, with a fixed numerator, this overall fraction will get smaller and smaller. In fact, we'll call that limit 0. 5 minus 0 is 5. Let's move to our second limit, and it's going to work pretty much the same way. Top of the screen, the limit as x approaches infinity for 3 over e to the x. Let's take the limit of each part. Limit of a constant stays 3. Limit as x grows to infinity for e to the x. We looked at that graph a few slides ago. That does not exist because it gets larger and larger without a cap. Fixed numerator, a growing denominator, limit of 0. Now let's look at a couple different limits involving sine. The first one is just the function sine x. As x gets infinitely large, sine of x, remember how it looks. It's a graph that oscillates up and down over and over and never stops. As x keeps getting larger and larger, your graph will continue to alternate and oscillate up and down. It never finds a true fixed value that it's equal to. So this limit does not exist. There's no finite number that your graph takes on when x is really, really large. However, when you take that sine function and you give it a denominator of x, excuse me, we're going to find out that this limit is 0. Let's investigate. At the bottom right of your screen, I've snipped in a portion of the graph of sine x over x. Because the sine x part oscillates back and forth from negative to positive 1, that one is a numerator that doesn't quite settle down, but it also doesn't get out of control with an infinity or an infinitely large value. However, the denominator, the larger it gets, the smaller the fraction becomes overall. So what you get with the graph of sine x over x is oscillating, decaying. That graph will continue to oscillate up and down, but it's like a dying wavelength. We can find this limit above using squeeze theorem. Sine of x has a minimum value of -1 and a maximum value of +1, and that's due to the amplitude of sine. We can trap our limit between two limits that are much easier to locate and find. I mean, not locate, but determine. For this left limit, a fixed numerator with a growing denominator has a limit of 0, and on the far right end, this limit does too. Fixed numerator, a really large denominator, will go to 0. So the limit of sine x over x as x approaches infinity has to be 0.